Hello, my name is Michal Przewozniczek from Wrocław University of Science and Technology, and I will present our research considering the hybridized linkage learning for permutation-based problems. I will first introduce you to statistical-based linkage learning and the quite recently proposed empirical-based linkage learning techniques. Then I will describe the paper objectives. I will give you the details of our propositions, the empirical linkage learning for permutation-based problems, PBEL, the new problem decomposition technique, and the hybridized linkage learning, which is the core of our proposition. Then I will show the results and summarize the presentation. The idea of statistical-based linkage learning is as follows. If we have a genetic algorithm, then in this GA we have a population of solutions, which is under the selection pressure. So what we can do is we can count the pairs of gene value frequencies, and on this base we can compute the entropy. Once we get it, we can create the matrix of gene dependencies called dependency structure matrix, and then we can use this information to improve the evolutionary search. The DSM is a square matrix which represents the dependencies between genes. And for instance, here, this entry represents the dependency between the first and the second gene. The greater we have the value, the greater two genes are considered to be. Here we have the example of DSM matrix for this population of 8 solutions for problem encoded on 9 genes. So, for instance, these two genes, gene number 2 and gene number 1, are highly dependent, and on the other hand, the 5th and the 4th gene, we have not found any dependency between these two genes. The DSM-based linkage learning and the statistical-based linkage learning, it was applied to many different search spaces, to discrete, of course, to binary and non-binary, to permutation-based problems, as in this work, in this research, and to continuous search spaces as well. Now, let's consider the empirical linkage learning. It's the idea, the reason of proposing it was that for some problems, the DSM-based linkage learning is imprecise. So we wanted to obtain a new problem decomposition technique, and it was recently proposed. It's significantly different than the DSM, the statistical-based linkage learning, and it successfully decomposes those problems which are DSM hard. Now, let's check how it works for the binary encoded solutions. Let's say we have an individual encoded on n genes. What we can do with this individual, we can disturb its nth gene. What we can do more is we can optimize the original individual with some greedy optimizer, and we obtain some optimized genotype. We can do the same operation for the disturbed individual, and now we can compare the optimization results. And on all positions in which the optimized individual and the optimized disturbed individual differ, we may assume that these genes are dependent on each other. Why? Because these differences were caused only by the perturbation of this single gene here. The information obtained from a single operation, which was shown here, is called a linkage scrap. So the technique I have just shown you is called linkage learning based on local optimization, FreeLO. It produces linkage scraps, which are the sets of genes which are dependent on each other, which were found dependent on each other. What is important is that FreeLO never reports the false linkage. The false linkage is a situation where when two genes which are truly independent, they are marked as dependent by your problem decomposition technique. And we support the appropriate proof in the paper, of course. Now, what's also important to remember is that FreeLO, as any other problem decomposition technique, it may overlook some dependencies. So when it misses the linkage, this is the situation when the two truly dependent genes exist and the dependency is undiscovered. Now, to summarize, the main features of FreeLO are as follows. It's precise because it never proposes the false linkage. However, its drawback is that it's computationally expensive. It seems to be applicable to any discrete search space. And the question is how to use it. You cannot use it in a typical state-of-the-art DSM using EAs because the optimizers which were proposed for the statistical-based linkage learning, they tend to update to frequently compute linkage, for instance, at every method iteration, and therefore free LO is not applicable there because it's too expensive. So to utilize it, the new EA was proposed, namely free LOA. And what's also important, the new propositions of empirical linkage learning are also given even this year on GECCO. They are faster, and what's even more important, they are more precise than the original free LO. Now, the objectives of this paper are as follows. First, we want to propose an empirical linkage learning technique for permutation-based problems, and then we want to hybridize the empirical and statistical-based linkage learning, and our objective there is to emphasize the pros of both techniques and reduce their cons. So how PBEL works? Let's say we want to check the dependency between the first and the fourth gene. We obtain an individual. It's encoded with the use of random keys. So from this encoding, we obtain the order encoded by the genotype. And we want to check the dependency between the first and the fourth gene. So what do? We modify the order of the genes in a way so these two genes are adjacent, and we do the first fitness check. Then we switch their places and do the second fitness check. Now, if these two fitness checks are not equal, they are different, then we say that we have detected the dependency between the first and the fourth gene. If they are equal, then we say, okay, sorry, there is no detection here. So what's important about PBEL is that, well, it does quite a lot of fitness checks. So it's expensive. Therefore, we are going to use it just once. Just before the optimization run, we are going to execute it and build the model of problem decomposition. However, what's the advantage of PBEL is that it's precise. So same as other empirical linkage learning techniques, it never reports the false linkage, and the appropriate proof we support in the paper. Now, as I said, the PBEL is precise but expensive. On the other hand, the statistical-based linkage learning is relatively of low cost, and it was shown already. It was shown useful for various problems. Another thing is that the results for binary search spaces, for instance, they show that empirical and statistical-based linkage learning, they may be suitable to decompose different kind of problems. So the idea is, let's join them. Let's join these two techniques, two types of techniques, create hybrid linkage, and then we hope to emphasize pros and reduce the cons. So how do we do that? We get the DSM from PBEL. It's built only from zeros and ones. So the zero here says we have not detected any dependency between the fifth and the third gene. And on the other hand, the one here says, okay, genes number 1 and 2 are dependent. On the other hand, we have the statistical-based linkage learning DSM, which gives us all the strengths of dependencies computed on the base of the entropy. So we say, okay, we think that gene number 1 and 2 are dependent. And we join them just by adding them. So you may see that since PBEL is precise, so if it finds the dependency, you are certain that the dependency exists. Therefore, the information from PBEL is the dominating one. The statistical-based linkage learning, the SLL, rates the strength of the dependency, and what is also important, it's relatively cheap, so it's computed frequently, and it supports the linkage diversity, which is also important because the recent works show that if you want to optimize many practical problems, real-world problems effectively, you need to use many different linkages. You cannot just have one perfect linkage and that's all. We are going to consider in our research two linkage learning based methods dedicated to permutation-based problems, the LT-GOMEA and the parameterless population pyramid for permutation-based problems, P4. They were both proposed quite recently and they were both shown effective. In our experiments, we will consider statistical, empirical, and hybridized linkage learning. Additionally, we are going to consider the random linkage, just to show that the problem decomposition is important and effective. We consider three different groups of problems: the permutation flow, shop scheduling problem, PFSP, linear ordering problem, LOP, and the ordering deceptive problems. So, first we show you the comparison between linkage learning and randomly generated linkage learning. For PFSP, the situation is very clear. For both methods, the standard and hybridized linkage learning is significantly better in all the runs than the random linkage learning. The situation may be surprising for the comparison between empirical and random, because in general for LT-GOMEA random is better and for P4 they are all more or less equal. However, these results are expected, and I will explain just in a second. For LOP, for P4, the standard and the hybridized linkage learning are definitely better than the random. Also empirical performs quite well when compared with random. For LT-GOMEA, the situation is quite different because LT-GOMEA does not seem to be very suitable for solving LOP. Here you may see that the random linkage performs better than standard and hybrid, although the empirical linkage learning is better than the random. So, to summarize, if we use people alone, it's frequently outperformed by random for LOP and PFSP. It's an expected result because P-bell is a static information. It's computed only at the start. So it's not diverse, and we need to have many diverse linkages to be successful. Therefore, for PFSP, hybrid and standard linkage learning, statistical-based linkage learning outperform random. However, random is maybe better than just pure empirical one. For LOP, the situation is a little bit more complicated. Hybrid and statistical-based outperform random for P4 definitely. For LT-GOMEA, the situation is actually dependent a little bit on the test case. The reasons are as follows. Well, first, P4 better preserves the population diversity, and LT-GOMEA may lose population diversity due to the fact that it maintains diverse linkages, but not as diverse as in P4. And this is the reason of why for LOP we are not that successful for LT-GOMEA. For deceptive problems, the results are here. So you may see that all these purple and red lines represent hybrid and empirical linkage learning. They are definitely, by scale, definitely the best for both methods. The standard linkage learning is also makes a difference for P4 and for LT-GOMEA. And random linkage learning is actually ineffective, which is quite obvious for this type of problems. So for both methods, the linkage learning based, those techniques which include empirical linkage learning, include people, they work significantly better. The statistical-based linkage learning, well, it's better than random, but not that good as the empirical one. And the reason is quite obvious. P-bell very precisely recognizes the problem structure, which is important here. Well, now we are going to compare different types of linkage learning. So for PFSP, you might see that the hybrid is basically equal to standard for both methods, and the hybrid is actually better than pure empirical for both methods as well. As well, the same situation is for standard. So standard is better than empirical for both LT-GOMEA and P4. The situation is a little bit different for LOP again. So hybridized linkage learning is better for P4 and for LT-GOMEA. However, when we compare hybrid and with empirical, for LT-GOMEA, empirical is better. For P4, the hybrid is better. So this is a slight difference. It is actually quite unexpected result that P-BEL is the best version for LT-GOMEA, and it definitely requires further investigation. This is the fact we cannot, we don't know how to explain. We are checking this up. So the general comparison of all these problem decomposition techniques is that hybrid linkage learning is the best choice for LT-GOMEA for PFSP. For LOP is a medium choice. For deceptive LT-GOMEA is also the best choice. So hybrid is the best choice for actually almost all of the cases. But even for LT-GOMEA, it is better to use hybrid than standard. So we may state that the hybrid linkage learning joins the pros of joint linkage learning techniques, which was our objective. And here we have some results when we compare these two methods with EDAs, which are quite fresh and were shown effective. The RK EDA and GM EDA, you may see that both LT-GOMEA with hybrid linkage learning and P4 with hybrid linkage learning, they outperform these EDAs significantly for medium and relatively short test cases. For the longest test cases, they definitely outperform GM EDA, but RK EDA is simply better. Which still means that their effectiveness is quite high. So to summarize, we have proposed the hybrid linkage learning, which seems to preserve pros of joint linkage learning techniques, and we think, in our opinion, the results we have shown you are quite promising. For both significantly different linkage learning based methods, we get relatively high results quality, not only for the PFSP but for other problems as well. And the hybrid linkage learning has increased the robustness of both methods, so they both can solve a wider range of problems. Thank you for your attention.